Most of what we've done in Math 133 so far, probability aside, has been working with means. What's the average and what's the standard deviation from that average, that kind of thing. But we need to talk about another really important aspect of statistics, and that is proportions. Proportions come up all the time for you. You might not realize it. So, for example, what proportion of people are going to vote for Barack Obama in the next election? What proportion of people are going to, I don't know, vote for Proposal 2 out of 10 in the next election? That kind of thing. So, you want to be able to find those proportions, and then we're going to have to be able to talk about those proportions and how they work overall. So to do that, we need to lay a foundation, a theoretical foundation, if you will, for how this is going to work. And that's what A2 is going to work for us. To be honest with you, we touched on it just a little bit in Chapter 6, namely 6.2, especially the binomial distribution, is also laying the foundations for how this is going to work. So to lay that foundation, we're going to do an experiment. Namely, we're going to look at a box that contains red and white beads. It's actually beads for us, not beans, but whatever. And I have a picture of it right here. It's from right here on my website, my personal website right there, image 1, 2, 3, 4. These are the beads. So bead 1 is the box on my counter in my office. There they are. So now this is a metaphor. I know you're not going to really, get a bead box in general. But this is a metaphor for a much larger thing. So suppose this was, I don't know, all the voters in Jackson County, all the voters in Michigan or something like that. What proportion of them are going to vote for, say, Obama's the white ones and Romney's the red ones? So what proportion is that? That's what you really want to know. You're not going to poll every single person, right? But you're going to get a group of them. I mean, what if this was, I don't know, leopards, all the leopards in the world, and the red is the ones that have this disease or this genetic marker on their DNA or something like that. Or the box is a metaphor for, I don't know, all the amoebas in I don't know, on the cover of something or in this little drop of water. So these are all the amoebas, and the red ones are the ones that are, I don't know, have a virus in them, that kind of thing. Okay, so I know the bead box is kind of silly, but it's a metaphor for how we take samples, how we take polls. It's a metaphor for all polls. Okay, all right, surveying and polling, if you will. Okay. So it contains red and white beads. Think of it as the population, right? There's a true proportion in that box of red. That's the population proportion P. So as a class, what we're going to do is we're going to take samples, one per student, and you're just going to have to imagine this. I have my face-to-face students doing it, and use the sample proportion that we find to estimate that population proportion. Okay, so let's think about this. So just by looking at the container, so go back and look at the box. What proportion of those beads do you think is red, or do you think are red? Well, I guessed 0.25. You can guess whatever you want. Guess, 0.23, guess 0.15, guess 0.33, whatever. So look at the box and kind of guess what you think it is. All right. Now, how close do you think your estimate is to the true proportion? All right. That is, how confident are you in your estimate? And the answer is you're not confident at all. In fact, you're 100% sure that you did not guess the true proportion, right? It's not really 25% exactly, but it should be close to 25%, right? You think? We're not sure, but we think it should be somewhere around there, right? Okay. All right, so now how could you be more confident that your guess is actually correct? And quite frankly, how could you get a better guess? Well, you could take a sample and count the number of red beads. So that's exactly what I did. And what all the students in my class do. They each come up and get a scoop, see, a little scoop full of beads. They carefully take it back to their desk and they count. Right? They separate the whites from the reds and they count them. Okay? All right, so we're going to take a sample and we're going to count. That's what we do with polling for, votes and stuff. They don't go poll every single person. They take a scoop of people, right? A random scoop. Or they don't go every leopard on the planet. They get a scoop of leopards, right? They, put some to sleep, not to sleep in terms of putting them down. It's a euphemism for killing them. No, I mean, they just tranquilize them and then, take a little bit of their blood and then let them go, right? That kind of thing. Okay. So It'd be really bad if they had to kill all the leopards to find this out, right? Okay, so they take a sample and they count, right? They figure out whether those leopards have that marker, or they figure out whether these people are going to vote for Romney, or etc. Okay, so we use the cup, we carefully scoop, and we get a proportion. Now, I don't honestly know if this was from this picture or not. It might very well not be, but just for the sake of it. So say we got 35 red beads, and then there's a total of 190 beads total. What's the sample proportion? So the sample proportion from your scoop is 35 over 190. That's x over n, which is 0.1842. And for the love of goodness, put this formula right on your note sheet. It's super simple, but don't forget it. You know, your sample proportion is equal to your value number that had what you wanted divided by the total. So for example, if this was the number voting for Romney out of the total, or the number of leopards that had that genetic marker out of the total number of leopards you look at, that kind of thing. Okay. Now, do we think that the true proportion, what it actually is in that box, is close to that proportion from our sample? Well, sure. I mean, as long as we took a random sample, or we assume that Alana did and I didn't rig it, then that true proportion should be close to what I got from that sample. Okay? So now let's list all the sample proportions from a class. And you're just going to have to bear with me. This was from a group of students of mine. This is what they got. So there are the numbers right there. You can just pause the video and write them down. As a matter of fact, you're going to need to have them in Excel. So you might as well take a moment. Here, I'm going to insert so you can't see this part, right? We'll get there in a second. But you're going to put them all right here, right? And I actually already sorted them in order, but you don't have to do that right from the beginning. But there they are. Put them down, type them into Excel, write them on your note sheet, and then type them in because we're going to need them. All right. Once you're done, then we'll go move on. So we're supposed to construct a frequency or grouped distribution in the table below using a class width of 0.01. So that's kind of what I made disappear over here, but I'll bring it back. I've already made this video once and my computer ate it, so I'm having to make it a second time. It makes me very happy. Okay, so we're going to start at 0.15 because I figure my lowest number is 0.153. Oh, and just on the note, when I typed all these in, then I clicked data and I clicked A to Z, and that's what put them in order from lowest to highest right there. Okay, so 0.15 seems like a good place to start. And I can see I've got two of them in the 0.15 area. And because I made my class with 0.01, the next class starts at 0.16, which is 0.01 higher than 0.15. Remember this from, chapter 2, right? So 0.16, there's 3 of them in there. 0.17, there's 2 of them, and so on. So there's all your classes. The highest we get is 0.267, so that's right down here. And then I highlighted all of this, clicked Insert, Column, picked a column chart, and then deleted the frequency, delete that title, I don't really need that. I don't like this design, so let me go down here and make it that design. And I right-click, Format Data Series, and I'm going to make the gap width 0. I want my border color to be black. And I want my border style to be much wider. That's just me. I like it a little bit thicker. There we go. Ta-da! Should look very familiar. We did this way back in chapter 2. Okay. So again, the class width is 0.01. Remember, class width is the distance between 0.15, 0.16, 0.17. Notice it's equal to that number plus 0.01. Remember that from chapter 2, right? So if these are the lower class limits, that's how we get them. Lower class limits, if you're interested. And then the higher class limits, the upper class limits, are the number right below 0.16. It's technically 0.159999999, but we never bother writing all that. Okay. Done with that. That's how I got those. Everything's grand. I copied and pasted back in here. Right? Put those in. That's my grouped distribution. Used a class width of 0.01. Again, that's the distance between these values. I drew a histogram. Ta-da! There it is. Don't worry about the arrow. We'll talk about that in a second. All right, now, roughly what kind of shape does this have? Well, it's not really any shape at all. It's kind of lumpy. it's maybe a little bit symmetric, maybe a little bit skewed left. Ugh, it's just terrible. So it's a crappy shape. We don't know what it is. It's nothing good. All right, now where is the center? That's kind of where I put that arrow. I mean, if you imagine this bottom line down here was a balance beam, right? Or this is a seesaw, a lever, or whatever. Where would you put the fulcrum, the center? And it's, I don't know, somewhere in here from 0.20 to 0.219, somewhere in this region, someplace. Okay? All right. So then I needed to find, and I wrote that roughly between 0.20 to 219, somewhere in there, and I put the little arrow for it. I guess if I want to explain, it's because that's where the graph seems, the histogram, I should say, seems to be balanced. Right? Remember, the mean is the balance point. Now, what is the mean for our class? Well, I found that right here. So the mean of the p-hats, because each one of these is a sample proportion. Some student had this p-hat, some student had this p-hat, and so on. The mean would be the average of them, right? So I type equals average, and my cells were A2 to A29. Enter. Hopefully you can see that. A2 to A29, like that. Okay? All right, so then I found that. I put that right there. Matter of fact, I'll put it right here. Copy, paste. Okay, so there's the mean of the p-hats, 0.206. Now, which do you think is closer to the true proportion, what it really is in that box? Your single sample, which was 0.1842, or the class average, which is 0.206? Think about it for a second. Hopefully you choose the class average because there are more samples taken, and so that's going to be more accurate, right? Doing it more times, taking more polls, pulling more data is going to be better than just one group, one sample, one poll. That's what I mean down here, right? The common phrase, the wisdom of the crowd is smarter than the wisdom of the individual, is greater than the wisdom of the individual. Our p-hats are not as accurate, our single p-hats are not as accurate as when we work on our own than when we work at a group, right? Because we only get a small sample, right? But when we average out all of us as a group, then what's going to happen? Some people got low scoops, right? Low proportion red scoops. Some people got high proportionally red scoops, right? Some people had a lot of red beads, some people had a few red beads, but they'll all balance out, right? And that's better than any one scoop would be, right? That's why when you lead up to, an important election like the presidential election, they're polling all the time. CNN's polling, Fox News is polling, everybody's polling like every day, every week they do new polls. Why? Well, because they're trying to get more and more and more scoops, right, to get a better sense of it. Of course, there's also the problem that the proportion of red is changing all the time in the background. But that aside, they're trying to get better and better and better at pictures of what's happening. Okay, so to avoid sampling bias, if you were in my class, how would you do that? If you were actually taking that scoop? Well, your eyes tend to get drawn to red, so we tend to get more red in our scoop than we really should. So you could blindfold yourself or close your eyes when you take the scoop. You can make sure that all your scoops are around the same size. Nobody takes a big gulp size or whatever, that kind of thing, right? So you don't just search for the red. Since many people were moving the beans at once, what does this say about independence? Okay, so just imagine from this box, what happens in the classroom is that everybody comes up and takes a scoop. So what's that going to do to your independence? So technically that's not independent because people took them back to their seats to count them. It's not random and unbiased every time. What I scoop out affects what's left for you to scoop out, and so on. So it definitely could affect the outcome if you keep drawing and keep drawing. But we take such small samples. Hold on one second. All right, that's why we take such small samples in relation to the size of the entire box. It's a really big box full of tons of beads. And so the little scoops don't really affect it. And so what we're going to say is, yeah, it's not independent, but it's independent-ish, right? As long as that we have our scoop size, little n, is smaller than 5% of our capital N, the size of the number of the beads in the box, we'll say we have independence in quotes, meaning it's close enough. Let's stop right there and I'll pick up right here next time.